Hello everyone. In this video we will continue to examine topic 7.2 nuclear reactions. Alright, so now that we have sort of dealt with the very high level abstract sort of interpretation of mass energy equivalence, we're going to come back to mass and actually sort of define some very useful, very practical things. Okay, so I'm going to come back to this concept. And ultimately where we're going is we're going to have to deal with nuclear reactions and sort of study those, figure out how they work. In a nuclear reaction, we will be dealing with very, very small masses. And it's useful to have a small mass unit to take care of that. So the unit that we're going to use is the Unified Atomic Mass Unit, written as U or AMU, depending on your system. And it's exactly equal to 1/12 of the rest mass of one atom of carbon-12 in its ground state. Notice this bit right here, which we haven't focused on before. In its ground state means in its lowest energy state, and you have to specify that, because if you don't, the mass is larger. It's in its ground state, and it's at rest. Okay, why 1/12 of one atom of carbon-12? Well, we've discussed this a little bit before, but in case you've forgotten, we would like the Unified Atomic Mass Unit as a unit to be conveniently around 1 for both a proton and a neutron. Now, why not just define the mass of the proton and the neutron as exactly 1U or 1 AMU? Well, first of all, they're slightly different from one another, which means you'd have to pick one. But moreover, that would actually be a little bit inconvenient for reasons we're about to see, because it would render virtually every other atom an annoying fractional part away from even. And carbon-12 is kind of in the middle of the atoms that we use. So we use carbon-12 as sort of this fundamental, or in this fundamental definition, so that the mass of a hydrogen atom will be a little bit above that, and then the mass of a proton or a neutron in a higher mass atom will be a little bit below that. And we'll see sort of how that works moving forward. Straightforwardly, at least for now, 1U is equal to 1.661 times 10 to the negative 27 kilograms. So if you're just trying to convert back and forth, that's how you do it. Now remember, mass is equivalent to energy, and mass is a measure of the energy content of the system. E equals m naught c squared, and c squared is huge. Okay, so we can ask, what form? That is, where is it exactly? If we're going to say that the mass is equivalent to the energy, you have to be a little more specific. What type of energy? Is it kinetic? Is it thermal? Have we somehow missed it? And the answer is, well, we have missed it, actually. We haven't talked about this yet, but the short answer is that the energy equivalence of mass, that is, if you take that mass and multiply by c squared, you get a huge amount of energy. That energy is in the form of the nuclear binding energy. It is the energy that binds the nucleus together, and we're going to see how that works in the next video.